Yes, welcome to this session on thermodynamics, that is basic thermodynamics. We will learn here we will learn properties properties of pure substances. So this chapter will make a strong foundation for understanding the steam power plant or steam turbine, right? So let's try to understand it properly. So suppose we have a liquid, suppose we have a water at 20 degrees Celsius, and we want to convert this water into 20 degrees into 200 degrees Celsius of steam, right? So you can see there will be the phase transformation will happen. So first what is going to happen, this 20 degrees Celsius liquid will convert into 100 degrees Celsius of liquid. Then what will be happen, then 100 degrees Celsius of liquid will be converting into 100 degrees Celsius of vapor. This is what phase transformation. This is what we will provide some sensible heat, and here in phase transformation some latent heat will be provided, right? Then what will be happen, then we will heat this 100 degrees Celsius vapor into 200 degrees Celsius of vapor. So again we have to provide some sensible heat. Sensible heat ये वहाँ पे आता है जहाँ पे टेम्परेचर डिफरेंस रहता है, राइट? सो नाउ लेट्स ट्राई टू ड्रॉ all this phenomena on TS curve. This is on y-axis we have temperature, x-axis we have entropy, right? So here what is going to happen, so I think, okay, so you can see at this point we are having water at 20 degrees Celsius. Okay, so then what we are doing, this is position 1, right? This is position 1. Then we are increasing its temperature up to 0.2. So this is what 0.2, right? This will be what 100 degrees Celsius. Okay, then what is happening, on from 100 degrees Celsius liquid it will be converting at the constant temperature, it will be converting to this point. This is 0.2, this is 0.2. Then again from 0.2 it will be converted into 0.3. Okay, so this point, it is what 100 degrees Celsius vapor, and again further heating, what is going to happen, we will get this point 0.4, this is 0.2, this is 0.3, then again this is 0.3, and we will heat this up to 4. This 0.4 is taken as 200 degrees Celsius. Okay, so here we will get 0.4, we will get here, this will be what, vapor. This 3 point will be in liquid, uh, in liquid region, right? No, sorry, this point 3 is state of vapor. Okay, so this phenomena is happen at one constant pressure, right? So on this line, pressure is constant. On this line, pressure is constant. Okay, now what is happening now, if I increase the pressure on this liquid, if I have increased the pressure on the liquid, so we have learned in the class that on increasing the pressure, on water, the boiling point of the boiling temperature of water increases. So what is going to happen? So if I will increase the pressure, then what will be happening? So we will get something point, we will get this point here and this narrower point here, and we will get this point here. Now again I am increasing the temperature, I am increasing the pressure. So this is another constant pressure line. So this is another constant pressure line. This is what, P2 equals to constant. Now again if I increase the pressure, this curve will shift here, it will come shift here, and we will get some point here, right? The starting point, let's take it is here. Okay, so just draw these lines. Okay, now you can see P3 is constant, right? Now you can see if I increase, this is what latent heat, now you can see there will be some point where, so you can see on increasing the pressure, this region is decreasing, the length of this region is decreasing. So I hope there will be one point where we will get one curve like this. So what is happening here? In this pressure, at this pressure, right, this is called pre-critical, P critical. So at this pressure, what is going to happen? If I heat a liquid, right, it will directly convert it into vapor. It will be directly converting into vapor. Now if I draw these lines, we will get one curve like this, and we will get one curve like this. This will be not a sharp corner, this will be having curvature, right? So this is the generation of this PV dome, right? So this line is called saturated vapor. This is saturated vapor line. This line is called saturated liquid line, and this point is called critical point. So what is going to happen here? At this point, saturated liquid line and saturated vapor line is going to meet. So this point is called a critical point. Now again, let's try to explore. At point 1 we will have only liquid, okay? At point 2 at point 2, uh, at, at point 2 at point 2 now we are increasing the temperature from 20 degrees Celsius to 100 degrees Celsius, and we know 100 degrees Celsius is the boiling temperature of the water. And on point 2, what is going to happen? First bubble of vapor is going to form from point 2. Then again at this point, what is going to happen here? At this point we will get 50% of vapor and 50% of liquid. And now what is happening at point 3? What is happening at point 3? At point 3, the last bubble, the last drop of liquid will be converting into vapor. Okay, so beyond the point 3 we will have all the vapors. Okay, and we are assuming that this point is in between these 2 and 3. That's why this region is called wet region. Here we will get what? Vapor and liquid, both phase we will get here. So this is in brief about TS curve for water. Right now let's explore it more in next slide. So here now let me draw this again. So we have drawn a line like this. This is T, this is S. This curve is, this point is critical point. This point is critical point. This line is what? Saturated vapor. This line is what? Saturated liquid. Okay, and now let's take, this is temperature T1. This we call T saturation, right? And let's take this temperature as T2. Let's take this temperature as T2. Okay, so here we get degree of subcooling will be how much here? T saturation minus T1. Now let T1 is 20 degrees Celsius and T saturation is 100 degrees Celsius. So what will be degree of subcooling? This will be 100 minus 20. It will be 80 degrees Celsius. Okay, now let's, for this reason we will get degree of superheating. This will be what? T2 minus T saturation. Let's take T2 as 200 degrees Celsius. So this will be 200 minus 100 equals to 100 degrees Celsius, right? These are the some important concepts. And here in this zone we will have liquid. In this zone we will have liquid plus vapor. In this zone we will have only liquid, right? So this reason degree of subcooling, this is called also subcooled region or undercooled region. This region will be what? This region will be subcooled region or undercooled region. Okay, where where we will get this range will be subcooled region. Okay, now let's explore it more. Now if we have some point here, this is what? Liquid, this is vapor. Now at this point what we will observe? we will observe the presence of two phases here in sorry so here we will have liquid and here we will have vapor molecules. Okay, so this is for liquid is coming from here, right, and vapor is coming from here. At this point we have combination of liquid plus vapor, right? This region we call this region as wet region. We call this region as wet region, and we do not apply ideal gas equation, that is PV equals to MRT, in wet region. We do not apply this equation in the wet region. Okay, so this is the one important concept, because this is applied for ideal gases. It is not for the mixture of vapor and liquid. Okay, now let's explore it more. So here we have some concepts, that is sensible heat, we know that Q equals to mc delta T. So the heat which is generating because of the difference in temperature, so this is called sensible heating. Okay, and another point is latent heat. This is latent heat. Now if I draw the TS curve, okay, so what we observed, that we observed a vapor, we observed this PV dome. So this will be what? Okay, this region where the phase transformation is taking place at constant temperature. Okay, so this region is called latent heat. So this line we term it F, and this line we term it as G. Okay, G for gas, F for fluid or liquid, right? So this is the standard notation, so we denote it like this. So here latent heat will be heat required for phase change. So let's denote it by QP. Then latent heat will be what? This will be DH. This is what? Specific enthalpy. This will be what? Hg minus Hf. This is what? Hg minus Hf, and we call this as HFG. This is latent heat. If liquid is going from here to here, this is latent heat, right? And similar thing we can explore if this is TS curve. So we know that area under the TS curve gives the heat, because we know change in entropy equals to what? Del Q upon T. So del Q will be equals to, for reversible process, TdS, integral TdS, right? So here area under the curve of this TS curve will be what? It will give latent heat. Now let's try to write this. So here we will get latent heat in terms of entropy. right? So we can write this latent heat in terms of entropy will be what? This is T saturation, T saturation, T saturation into this is SF, this is SG. Okay, so we will get SG minus SF, SG minus SF. This is what is specific entropy. Okay, and this will be equals to T saturation into Sg minus Sf. We can take entropy also or specific entropy, right? But the unit will be different, correct? So here this will be what? Here unit will be different. Make sure this point, right? If we take this, unit will be, what is the unit of entropy? Kilojoule per Kelvin. If I take this, unit will be kilojoule kg Kelvin. Okay, so both relations this will be equal to this. So this is the general relation for latent heat. Now one important point, now if you can see from this figure, you can see from this figure, as the pressure is increasing, as the pressure is increasing, right? So this difference is going to reduce, this difference is going to reduce, right? So at this point, at critical point, latent heat will be zero, because the change in, these are the point function, right? So change in enthalpy or change in entropy will be zero at this point, right? So this is all about sensible heating and latent heat. Okay, now let's move to another section. So here now one important concepts come, which is called dryness fraction. So this is what dryness fraction. So if I draw a PV curve, sorry, TS curve, right? So this will be what? Correct. So this is liquid region. We go from here to here, we will get vapor region. Okay, now here we define, this is here guys, this is horizontal line, this is horizontal line. So this is liquid, this is vapor, right? So we define a term, and this is the wet region, this is the wet region, this complete region is the wet region. And at this point what will be there? So we have seen earlier, so here at this point we will get liquid plus vapor, right? Now let's write here, now let's define one physical quantity, that is x. This is what mass of vapor, this is what mass of vapor upon mass of vapor plus mass of liquid, okay? So this is dryness fraction, right? So we defined the dryness fraction like this. Now can you tell me what will be the value of dryness fraction at this point, right? So here you can see, if I explore this, so what we will get here, we will get here only liquid. Okay, so here we will get only liquid. So mass of vapor will be 0, mass of vapor will be 0. Check x will be what? X will be 0. Okay, now let's take at this point what is going to happen. At this point what is going to happen? So here we will get complete vapor. Mass of liquid will be 0. So here x value will be 1. Okay, now let's try to draw these are different dryness fraction curve. Now you can see if x equals to 0 here, then this curve will be for x equals to 0.1, this curve will be for x equals to 0.2, and this curve will be what, x equals to 0.8, this will be x equals to 0.9, and this equals to what, x equals to 1, right? Now you can see what will be the dryness fraction at this point, at critical point, right? So here dryness fraction is not defined because we don't have any limiting concentration of mass of vapor and mass of liquid, right? So this is all about what dryness fraction. And similarly we define a specific volume of mixture, right? So here if you do all the derivation, we will get v equals to, this is what f line, this is g line, vf plus x vg minus vf. This is what specific volume of the mixture. This is defined for wet region. This specific volume is for wet region. Now what you do, just put the x equals to 0, then we will get what, volume of liquid. Put x equals to 1, we will get what, vg. This is a specific volume. How we define specific volume? Volume of fluid or matter upon mass of the fluid or matter, right? So this is, now let's explore more. Specific properties. Okay, so let's try to explore this. So we have, as we have drawn earlier, we will get one TS curve, and this TS curve will be like this, right? So here we have liquid, this is liquid plus vapor, this is vapor, and this line is F, this line is for G. Okay, here what will be happen? So we have written that a specific volume in wet region, this is defined for wet region, it will be equals to what, Vf plus x into Vg minus Vf, right? So similarly we write specific enthalpy at this region will be equals to Hf plus x Hg minus Hf, and we write entropy, specific entropy at this region will be Sf plus x Sg Sg minus Sf, right? And internal energy at this point will be what? Uf plus x Ug minus Uf, right? So here one important point comes when we take when we take when we consider superheated vapor as ideal gas, right? Superheated vapor as ideal gas. So we assume superheated vapor as ideal gas. This phenomena happens at low pressure, right? So at low pressure, we will take this region as ideal gas, and we will consider this region also as an ideal gas. So what do we mean by ideal gas? If ideal gas, it will be ideal gas. So what we can write? We can apply PV equals to MRT in this relation, right? And what we can apply it? We can apply all that Q equals to mcp dt, and we can apply TdS equals to dH minus VdP, TdS equals to du, this is capital H, du plus PdV. We can apply for these things. Okay, so now let's explore it more. Now let's write enthalpy at enthalpy at various points. Okay, now let's draw the TS curve. Okay, so we will get something like this. Now let's take point 1 here, point 2 here, and point 3 here. Okay, let's see what is going to happen. And this will be what? This is F line, this is what? This is G line. Okay, now let's write enthalpy at 1. This will be what? HF. This is what? HF. We will get HF, and this will be minus Cp liquid. This temperature will be Tsat, this temperature will be T1, and this temperature will be T3, right? So this will be what? CPL Tsat minus T1. Okay, we know that how we define enthalpy, right? We define, this is what? Specific enthalpy. Okay, this is small h is for specific enthalpy. So this will be Cp dt. So first we calculate the enthalpy at F, subtract this thing. Now how we define enthalpy at 2? Enthalpy at 2 will be how much? HF plus X Hg minus HF. Okay, this enthalpy at 2. Now enthalpy at 3, how we define this? This will be Hg plus what? Cp vapor into, keep this value as positive, T3 minus T saturation. Okay, so what you have to do, see here we have already written minus sign, So just keep this value as a positive, this value as a positive, this value as a positive, right? So we will get what? Enthalpy at various points. Okay, now let's explore it more. Entropy at various points. So just draw the TS curve. This is T, this is S. Okay, so just draw the points. Okay, now let's take this as a point 1, this as a point 2, this as a point 3, this is T set, this is T1, this is T3. Okay, and this is all happening at a constant pressure P, right? Now let's apply the TDS relation. TDS equals to dH minus VdP. Okay, now you can see on this line, on this line, pressure is constant, so this value will become 0. Okay, and this dH will become what? mc dt. And if I want to write ds, this will be divided by t, right? And just integrate this, integrate what we used to do. We used to integrate this mc dt upon t initial, t1 to t2, let's take is t initial to t final, right? And what we used to get as S final minus S initial equals to mc ln tf upon ti, right? So this is what change in entropy, and here we have considered this region, superheated region, as an ideal gas. Okay, now let's write the entropy for region 1, for point 1. So what we will get, we will get for point 1, we will get, okay, and if I write it in terms of specific entropy, this will be SF minus SI equals to C times ln TF upon TI. Okay, so now let's write the specific properties at different points. So let's write for 1. Okay, so this will be S1 will be what? SF, and here T, if okay, we want to come at this point, this will be SF minus C into, this will be C liquid into ln, keep this quantity greater than 1, T set upon T1. Okay, so if we are coming from here to here, so this will be what? T final, and this will be what? T initial, right? So this is S1, Now write S2 is what? So we have written earlier S2 will be SF plus X SG minus SF. Okay, and this thing we can also write it as SF plus X times, this will be what? Latent heat upon T saturation. This is for point 2, and let's write entropy at point 3. This will be what? This will be what? Sg. This will be what? Sg plus C into ln. What will be happen here at T3 upon T2? Keep this quantity greater than 1. Keep this quantity greater than 1. You will get answer very easily. Right, so this is all enthalpy and entropy values at different points. So these enthalpy at various points and entropy at various points, this is very important for your T2. So this is all for today.